Jnanam paramam dhyayam. Knowledge is supreme.
Now, the problem comes, we were all along lucky here. In the earlier example, we saw that eigenvalue lambda equal to 1, the nullity was 1. So, we could not find eigenvectors, that was not diagonalizable. There is a class of matrices where everything goes very nicely, and they are called the real symmetric matrices. So, the theorem says if A is a n cross n real symmetric matrix, then A has n real eigenvalues. See, what are eigenvalues? They are the roots of the characteristic polynomial, right. Even if A is a real matrix, the characteristic polynomial will be a polynomial with real coefficients. So, it may not have as many real roots as is the degree, but there will be as many roots as the degree, they may be complex, right. So, fundamental theorem of algebra says given a polynomial, either real or complex, does not matter what coefficients, it will have as many roots as the degree, but some of the roots may be complex roots, and we are given a matrix which is real. So, we are interested only in the real roots. So, the characteristic polynomial of a real matrix may not have real roots at all, that is also possible. It may have real roots, right, but not all of them roots may be real, some roots may be complex, right. But here is a special type of matrices which are called the real symmetric matrices. It says if A is a real symmetric matrix, that means a matrix with real entries. And what is a symmetric matrix? When you say matrix is symmetric, if A is equal to A transpose. So, if it has that property, then it says, the theorem says, for a real symmetric matrix, it will have n eigenvalues. That means the characteristic polynomial will have all roots real, right. They may or may not be repeated, that is a different story. They will have all, and hence there are n eigenvalues, that means there will be as many eigenvectors also. Each eigenvalue will give you an eigenvector, right. So, important thing is, for a real symmetric matrix, all roots will be real, okay. There will be as many eigenvalues as is the order of the matrix, that is very important, okay. So, that is, so how do you, let us prove it. So, we will start with the characteristic polynomial is a polynomial with real coefficients, right. So, let us treat it as a polynomial with complex coefficients, real numbers are part of complex numbers anyway, right. So, it will have roots which are probably complex, and we will say, we will show that each root of the characteristic polynomial has to be a real number, right. That is what we want to show. That means, if lambda is a root of the characteristic polynomial, then lambda is equal to lambda bar, where lambda bar is a complex conjugate. If we show that, then we are through. So, for that, so let us assume characteristic polynomial will have n roots, right, in complex numbers. So, let us take any lambda, okay, in C to be an eigenvalue, and a vector u, which, because if the scalar lambda is complex, when you write a minus lambda I, it is not sure that you will get a eigenvector with all real entries only, right. If lambda is complex, it will turn out to be complex. If lambda is real, then all row operations will give you only real only, right. So, if lambda is assumed to be a complex number, so we cannot say that eigenvector will be real. So, but at least eigenvector will be in Cn with entries as complex numbers. So, let us start with that. That means, A applied to lambda is equal A applied to u is equal to lambda multiplied by u, right. So, that is given to. So, we will show that this lambda is in fact a real eigenvalue. So, we have to show lambda is equal to lambda bar, right. That is what is to be shown using the fact that lambda is an eigenvalue. A applied to u is equal to lambda applied to u, only that fact is to be used. Now, in complex numbers, how is the dot product defined? That is what is going to be important. In Rn, the dot product is sigma ai bi, right? A dot b, if A has got components a1 a to an, b has got components b1 b to bn, then what is A dot b? That is just sigma ai bi. But if they are complex, then what is the definition of the dot product? Then just saying ai bi does not help, right? What you want us to do a modification is ai bi bar you have to put. You have to take the product ai bi bar, because there are two reasons for that. One, when you take dot product of vector with itself, you should get the magnitude. So, if b is equal to a and they are complex, right, then what is a dot a? That will be sigma ai bar, so that will be mod of ai square, right. So, you will get magnitude has to be real, right. So, if you do not put the bar, you will get ai, which is again a complex number. So, a dot a will be a complex number, which does not make sense. Is it clear? That is why the definition of dot product in complex entries is defined as, for a vector a with components a1 a to an, b with components b1 b to bn, a dot b is defined as sigma of ai multiplied by bi bar. Okay. So, that is the definition of the dot product, and then it has all the properties that dot product has. So, we will be using that. So, here is repeated again. So, if you write u as a column vector, if you want to write in terms of matrix multiplication, okay, then the dot product u dot u is nothing but u bar, right, y transpose, because you are writing as a column. So, you should write it as a row vector 1 cross n multiplied by n cross 1, the product should be a scalar, right. So, that is why this is in terms of matrix multiplication, and you see the bar coming here, right. So, the dot product is u bar transpose u as matrix multiplication of, if you are writing u as a column vector, just reinterpreting the dot product in terms of matrix multiplication when the entries are complex. That is the definition also. Okay. So, using that we will proceed. So, it is easy to see that with this definition, if you take dot product of ax and y, right, that is same as the dot product x with a transpose y. You can take a, and but that becomes a transpose in the other variable. Okay. So, that is easy to see from this definition. So, with this understanding, let us proceed. Lambda is an eigenvalue with eigenvector as u. So, let us compute lambda times norm of u square. What is norm of u square? Dot product of u with itself. Okay. Now, this lambda, because of linearity, I can bring it inside here, dot product. So, it is lambda u, right. But lambda is an eigenvalue, u is an eigenvector. So, what is this first term? That is a multiplied with u, right. And now, this a I will take it on the other side, okay, that will become as a transpose. So, u times dot product with a transpose u. But what is a transpose u? A is symmetric. Keep in mind, till now we have not used that fact that a is symmetric. So, what is a transpose? That is a itself. So, what is this term? This is again lambda of u, right. So, that is again lambda of u, but in the component dot product, when this lambda comes out from the second component, it comes out as a bar, right. So, this comes out as a bar u. So, you get lambda times magnitude of u square is lambda bar multiplied by magnitude of u square, but u is an eigenvector. So, it cannot be 0. So, this magnitude cannot be 0. So, you can cancel out both sides. So, lambda is equal to lambda bar, right. So, it is a simple property of the dot product in complex numbers, right. In Cn, the dot product is not just sigma ai bi, it is ai bi bar, right. That only gives you that the property that in the second variable, when you take lambda comes out as lambda bar, in the first variable it remains as lambda. So, those are the properties of the dot product for Cn. Okay. So, that gives you lambda should be equal to lambda bar. So, simply using the fact that only we have used symmetric here, right. A transpose is equal to A. This place we have used A is symmetric, otherwise it is just a definition of the dot product, nothing more than that. So, all the eigenvalues are real. So, this is a special class of matrices which says if A is real symmetric, then be sure you are going to get as many eigenvalues as is the order of the matrix, and all, if the matrix is real, you will get real eigenvalues, right. Okay. There is a corresponding result for complex also, but we will do it a bit later, probably just state it. So, if A is complex, what is the corresponding thing for saying A is symmetric? It is not just A is equal to A transpose, it is A equal to A bar transpose, you put it there. So, that is definition, and say you call it as Hermitian matrices, so that is the definition of A. So, a Hermitian matrix, if it is real, it is a symmetric matrix, right. And for that we will see what are the results, we will a bit later probably. So, for real symmetric, all eigenvalues, so eigenvalues will exist, because fundamental theorem of calculus says eigenvalues should exist, right, and this theorem says all eigenvalues have to be real. So, a n cross n real symmetric matrix will positively have n real eigenvalues, and hence n real eigenvectors also. Okay. So, and the corresponding eigenvector when you find, that will be a real eigenvector, because you will be solving that homogeneous system of equations, right. Okay. There is actually something more which happens. So, I think that also is simple, let us prove it today itself. So, if A is real symmetric and there are distinct eigenvalues, we have already shown that for any matrix, if the eigenvalues are distinct, then the corresponding eigenvectors are linearly independent. But now it says something more, if lambda 1, lambda 2, lambda k are distinct eigenvalues and you pick up eigenvectors corresponding to them ui, then they are not only independent, they form a orthogonal set, they are perpendicular also. So, you get a special property that distinct eigenvalues give you eigenvectors which are linearly independent for any matrix, but if the matrix is real symmetric, then the eigenvectors are actually perpendicular to each other. Okay. So, let us again, the proof just realizes the fact that what is the dot product in, right. So, let us just look at, so take any two I naught equal to j, and we are given A is equal to A transpose. So, let us look at lambda I ui uj. I am taking the dot product of ui with, what is my aim? Aim is to show that dot product is equal to 0. If I want to show them they are perpendicular, ui must be perpendicular to uj, means dot product is equal to 0. So, that is why I am taking ui uj dot product, multiplying with my scalar lambda I, the corresponding eigenvalue. This lambda I can take it inside. So, take it inside is lambda I ui, right. But what is lambda I ui? It is the eigenvalue. So, this is A applied to, right, it is A applied to ui, right. Now, this A I will shift it to the other variable now. So, I can shift it to other, it becomes A transpose, but A is symmetric. So, what is this A transpose? That is A itself, again the same idea is used. So, A uj, but what is A uj? That is lambda j, because it is an eigenvector again. So, it is lambda j, and this lambda j comes out, right, it is lambda j again. Why lambda j, not lambda j bar? Because real symmetric, they are real now, right, we already proved. So, and lambda I is an eigenvalue. So, what does this imply? I can cancel out lambda I, I already assume, right, with distinct eigenvalues. Okay. So, what does it imply? If I is not equal to j, lambda I, they are distinct, right. So, if I take it on the other side, lambda I applied to this is lambda j applied to this. Take it on one side, what is it? Lambda I minus lambda j applied to ui uj is equal to 0, but they are all distinct, right. So, the lambda I minus lambda j cannot be 0. So, what should happen? Ui uj dot product must be equal to 0, right. Is it clear? because these are distinct, lambda I is not equal to lambda j, I can take it on the other side and divide by that, because that is not 0. So, I get ui equal to uj, that is equal to 0, right. So, we get that the eigenvectors corresponding to the eigenvalues of a real symmetric matrix, if they are distinct eigenvalues, then the corresponding eigenvectors are not only linearly independent, actually they are orthogonal to each other, right. So, this will play a role later on, because once supposing all the eigen for a real symmetric matrix and distinct eigenvalues exist, right, we will get eigenvectors corresponding to them. We know that, see, for a real symmetric matrix eigenvalues will exist, they may be repeated, but supposing you are lucky and you get distinct, all distinct, right, then the corresponding eigenvectors will be orthogonal to each other, right, you will get as many. So, you will get a basis consisting of eigenvectors which are orthogonal, right, and if you divide each one of them by their norm, you got a orthonormal basis, right. So, for an ordinary matrix, if eigenvalues are distinct, you will get a invertible matrix, right, but if it is a real symmetric matrix and the eigenvalues are all distinct, right, there are n eigenvalues which are all distinct, you will get a orthogonal matrix which will diagonalize it. So, that is the advantage, right. So, I think we will do that next time. Upshot of today's thing is how to find eigenvalues, how to find eigenvectors. If you are lucky, distinct eigenvalues, you will get a matrix which is diagonalized, which will diagonalize it, and the important that happens because eigenvectors corresponding to distinct eigenvalues are linearly independent in general. When it is real symmetric, all eigenvalues will exist, there will be n real eigenvalues, and eigenvectors corresponding to distinct eigenvalues will be not only linearly independent, they will be actually orthogonal to each other, right. Okay. So, let us stop here today.